into this explainer and completely demystify the everyday science of light. We're going to be breaking down everything from why laser pointers shoot perfectly straight to why mirrors stubbornly reverse the text on your favorite t-shirt. Light is something we interact with literally every single second we're awake, yet we rarely stop to actually map out how it works. Well, today, we're going to change that. Here is our roadmap for today. We'll start with the ray model explained, move right into when light hits objects, dive into the law of reflection, learn about drawing a ray diagram, and then wrap the whole thing up with plane mirror image characteristics. Kicking things off with Section 1, the ray model explained. So, the absolute foundational rule here is that light naturally travels in perfectly straight lines, which physicists call rays. Think about that really sharp, straight beam you see if you shine a laser pointer in a dark room. That is the ray model of light in action. You just draw it as a straight line, slap a little arrow on it to show which way it's moving, and you're good to go. It's super simple, but honestly, it's the building block for literally everything else we're going to talk about today, because light, it just keeps going on this perfectly straight path until it finally crashes into something. Which brings us to Section 2, when light hits objects. Picture this. Our straight-line laser beam is cruising steadily across the room. But what exactly happens when it hits a solid wall, or a window, or a mirror? It obviously can't just keep going on its original path. Well, the universe basically gives light a few specific options when it encounters an obstacle. When light hits an object, it really has three choices. First off, it can bounce back. That's reflection, like looking into a mirror. Or, second, the material can physically take in that light energy, which we call absorption. Most of this absorbed light actually transforms straight into heat energy. It perfectly explains why wearing black clothes in the middle of summer makes you so ridiculously hot. The fabric is just absorbing all that light. And third, we have transmission. That's where the light simply passes straight through a transparent material, which is why we can see through things like clean water or a glass window. Moving on to Section 3, the law of reflection. Because we really want to figure out exactly how mirrors work today, we're going to go ahead and push absorption and transmission to the side for now. We're focusing entirely on that very first phenomenon, reflection. To really analyze a bounce, we've got to name our actors. The incoming light ray, the one actually striking the surface of the mirror, is formally called the incident ray. And the second that light makes contact and shoots away, it becomes the reflected ray. So incident ray comes in, reflected ray goes out. Simple enough. Now this is where things get kind of fascinating. There's this invisible concept at play here called the normal. You obviously can't see the normal in real life. It's an entirely imaginary line that we draw, exactly perpendicular, meaning at a perfect 90-degree angle to the mirror surface, right at the exact point of contact. Why in the world do we invent this invisible line? Because it gives us a perfectly straight, reliable baseline to measure all of our light's angles against. Using that imaginary normal line, we can mathematically map the entire bounce. The angle between the incoming incident ray and the normal line is called the angle of incidence, and we just represent that with a lowercase I. Then, the angle between the outgoing reflected ray and that exact same normal line is the angle of reflection, represented by an R. And that brings us to the ultimate ironclad rule of physics governing every single mirror you have ever looked into, the law of reflection. It states, very simply, that the angle of incidence I is always equal to the angle of reflection R. It is a perfectly symmetrical mirror image of angles. To put that into perspective, if an incident light ray strikes a mirror at exactly 40 degrees relative to our normal line, it has absolutely no choice but to bounce off at exactly 40 degrees. It's literally never going to be 39 degrees. It will never be 41 degrees. The universe demands absolute, perfect symmetry in this bounce. Let's dive into Section 4, drawing a ray diagram. Okay, so we know the rules of the bounce, right? Now let's actually draw it. A ray diagram is pretty much exactly what it sounds like. It's a highly detailed drawing that charts the specific path taken by light rays from a source, off a mirror, and straight into an observer's eyes. It's basically the ultimate tool for studying how mirrors, lenses, and even cameras function. It lets us mathematically predict exactly where an image is going to appear on a piece of paper. Building one of these diagrams is honestly just like mapping out a journey. We start by drawing our object in our mirror, and then we send out an incident ray. The very second it makes contact, we drop in our normal line to calculate the perfect bounce. But here's where the real magic happens. By bouncing another set of rays and extending all those reflections backward behind the mirror using dashed lines, we can see exactly where they intersect.
Now here is a really crucial point. Those dashed lines, they aren't actual light piercing through a solid wall or going through the glass. Light obviously doesn't travel through the back of a solid mirror. Rather, this is just a mathematical representation of an optical illusion. The point where those extended dashed lines meet up behind the mirror is simply where your brain thinks the light is coming from. That intersection point is exactly where the image lives. Which takes us to our final stop, Section 5, Plane Mirror Image Characteristics. Now that we've totally traced the precise math of the bounce and found exactly where the image forms, let's define the final illusion our brains actually perceive when we look at it. A standard plane mirror reflection has 4 specific traits. First, it keeps you perfectly upright. You obviously don't look upside down in your bathroom mirror. Second, it perfectly mimics your size. If you're tall, your image is equally tall. Third, it forms at the exact same distance. So if you stand 1 meter in front of the mirror, your image appears to be exactly 1 meter behind it. But then, there's the fourth characteristic, and this one introduces a major twist to our otherwise perfect copy. That twist is what we call lateral inversion. This just means the left side of the object appears as the right side of the image, and vice versa. It perfectly explains that everyday mystery of why the text on your t-shirt looks completely backwards when you look in the mirror. Your brain is basically seeing the light rays cross horizontally, flipping the whole image from left to right. So we've completely mastered the straight lines, the perfect bounces, and the upright, laterally inverted reflections of plane mirrors. But, this leaves us with a truly fascinating question to ponder. If light travels in perfect straight lines, and a mirror keeps an image perfectly upright, what kind of strange journey forces an image to turn completely upside down when light passes through a pinhole camera? Think about how those straight rays would actually have to cross to make that happen. We are going to be exploring that exact puzzle next time. Keep visualizing those rays, and I'll catch you in the next explainer.